So next up, I'm delighted to introduce Kathy Yu, who will be talking about how you go about training your novel model. Um, of the many parts of the research project, one of the most important, especially for deep learning research, is going about understanding and building on the training pipelines that you need to go about training a model. And this is a aspect of research that has evolved very, very quickly in the past few years. And our attempt here with Kathy's lecture is going to be to walk through a very real world example of a pipeline and how you might go about training your deep learning models and then keeping track of your experiments. So without further ado, I'm very excited to introduce Kathy Yu.
Thank you so much, Pranav, for the introduction. Hi, everyone. I'm Kathy. I'm very excited to be here today to walk you through this lecture. So let me start by sharing screen. Okay. Can people see my screen okay? Awesome, thank you. Okay, so without further ado, let's get started. So as Pranav mentioned, in this lecture, we'll be going through a practical example of how to train your own novel model. And there are a few learning outcomes planned out for this lecture. So the first is, I hope that after this lecture, we will all be able to identify the essential components that go into building a novel model. I hope that we can also learn how to train novel models from scratch, and beyond just writing the basic training script of training the model, I hope that we can also learn how to manage experiment configurations using a tool called Hydra, how to log model checkpoints that are being generated during the training process, how to manage and analyze potentially a large amount of experiment results using Google pivot tables. And then finally, I also hope that we can learn how to log metric values and other supporting materials, such as images, using a platform called Weights and Biases. And beyond these, I also hope we can develop a good understanding of the value of maintaining good code quality, of ensuring that our experiments are reproducible, and automating our experiments. And then finally, I hope we can all also walk away with a preliminary understanding of other best practices on training your model after this lecture. So what are the motivating scenarios that this lecture was designed for? So first of all, maybe you've never trained a model before. Maybe you've heard of really cool large models, and you can get model outputs from an open source library or API call. And maybe you want to know, if I want to do this on my own, if I have a cool idea, how can I implement the model architecture, and how can I properly train the model to get the intended performance? The other motivating scenario is perhaps you already have some experience in basic model training, but you might find that every time you start on a new project, you kind of have to rewrite all of your code because the earlier codes are becoming messy, or you no longer understand why you wrote particular sections of the code. So you always have to start from scratch. In addition, it might be hard to debug deep learning codes. So the other motivating scenario is maybe you want to learn how to write cleaner and reusable code. The next motivating scenario is perhaps you already know how to write a basic training script, and you also know how to write good code. However, with deep learning, a lot of times we have to do a lot of trial and error before getting the model that we actually hope for. And that trial and error process can be quite cumbersome, because during that process, you have to run a lot of experiment trials. You need to maintain a clear mind of what you've tried and what to try next. So managing experiments is also a challenging aspect of training your model. So this lecture is also designed to show you how to do that properly. And then finally, with knowledge of all of these, you might still wonder, how can I improve my model? How can I push the metric result to a better level? That is a very hard question to answer. And I think the most important thing to improving your model is actually understanding your model first, where it's doing wrong, where it's doing right, and then we can improve from that. So the last section of this lecture will focus on how to understand the model better in order to train better models. So here is the agenda for today. We'll start with an overview, and then we will look at techniques to tackle each of the 4 motivating examples next. And then finally, we will do a wrap up. We'll do a summary. So first, an overview. What are the essential components that go into building your own novel model? So first, we want to have an overall design. So what does this entails? So the overall design should include some kind of hypothesis that you're testing. For instance, one potential hypothesis may be, if I try this particular architecture in my model, would I be able to improve the performance of my model on a particular task? We also want to have an overall experiment plan. So this can cover a lot of things, including, for instance, what things you will try first, what things you'll try next, what is the overall timeline of your experiment. Also, we also want to have some success metrics. So we need to be able to evaluate whether we're doing the correct thing or not. And we also need to have a stopping condition that would allow us to say, oh, we are getting the model that we want, we should stop here, versus this model is still not up to our standards and we want to keep training. Lastly, we should also think about what are the constraints that we have in training this model. So for instance, maybe your intended task is to run this model on some kind of mobile device or in an edge setting. Then in that case, you need to make sure that your model can run fast enough and it's lightweight enough so that it can run in a reasonable speed on edge devices. So these constraints are also important to keep in mind before you start writing any code and doing any training. If we break down this design further, we also have a lot of logical components that are important. So first, we have the data. So how would you obtain this data? What format did the data come in? Do we have to do any reformatting before plugging the data into our model? We also need to think about the model design. So that can entail a lot of things, including what is the specific model architecture that we're using? Are we utilizing any pre-trained weights from other models for certain parts of our model? We also have to think about how we want to train the model and how we want to evaluate the model. So in terms of training, one obvious component is what is the loss function that you would train the model on? And in addition, what does the training loop look like? What different kinds of losses are you using and how are you combining the different losses? In terms of evaluation, it's also similar, but for evaluation, we also need to think about what specific downstream task we will test our model on and what are some representative metrics that we can compute for those desired tasks. We also have a variable set. So this set basically contains all of the things that we can tune while training our model. So for instance, we can tune our learning rate for the model, we can tune different optimizers, we can tune the different design, the different width and depth of our models. So all of those are considered part of the variable set. We also should have a plan for how we're going to analyze the results. So as I briefly mentioned earlier, we have different metrics that we can compute for the intended downstream task, but at the same time, we can also think about particular tools that we can use to visualize results, to aggregate results, so that we can properly assess how good the model is performing and how do we improve from that. And then finally, we usually need to have a bunch of utility functions. handy. So for instance, you might want to visualize your model outputs. You might have logging utilities that allows you to keep track of all of the intermediate values, the artifacts that are generated by your model. So yeah, on this page, this is a pretty big list of the things that you should start thinking about before building your model. And next, let's actually dive right into our live coding session. We'll look at a basic workflow of training your model. So let me switch to the notebook. So on this page here, you'll see the overall notebook for this live coding session. I will repeatedly switch between the slides and the notebook during this session. So in this live coding session, we will get hands-on practice on training the LBEF model, which came out of Salesforce. And specifically, we are looking at the Flickr 30K dataset and the classic vision language task of doing image text retrieval. And this session does assume that you have some prior knowledge in basic deep learning and basic PyTorch, but you don't have to have any prior knowledge of the tools that we'll be introducing, Hydra and some biases, for instance. The goal of this session is to teach you how to use those tools. And because of the limited time we have in this session, we won't be able to go into the very specific details of the code. We will be reusing much of the code from the LBEF GitHub repository, but that's okay. The goal here is to give you an overview of what are the necessary steps that you need to do for training your model, and we will implement all of the key parts together. For the other parts, feel free to read these after the session. Okay, so let's get started. The first step before we actually start our 5 steps of training your novel model is we need to do some setup. So over here, we're loading a notebook extension that allows us to modify Python modules on the fly. And then here, because we're using Colab, I am mounting this notebook to our Colab, to our Google Drive, and you can already see all of the files that we have prepared for this session.
Kathy, could you increase the font size, please?
Yeah, of course. Sorry about that. Is this big enough?
How about larger?
Okay.
Yeah, that looks good. Thank you.
Okay, thank you. Yeah, okay. So it's generally good practice to, if you're working from a Colab notebook, then it's generally good practice to mount to a Google Drive, because that would allow all of your changes to be persistent, so that in the future, you can also refer back to the modification that you've made in the notebook. However, if you're running code on a local machine or on a cluster, then you don't have to worry about that. Other than that, we want to prepare our working directory. So for instance, let's name this working directory AI research intensive and live coding. So this will be the directory where we put all of our code as well as data. And then, as I mentioned earlier, we'll be using code from the LBEF GitHub repository. So we will be cloning this repository into our working directory, and I have already prepared that beforehand. And we also need to install a bunch of dependencies that do not come installed in Colab. So we will go through these dependencies later on. So for instance, you can see Hydra, you can see weights and biases. And then we also have a script that allows us to install all of the necessary dependencies. So the key things here include the PyTorch modules, as well as a lot of modules, helper functions from the LBEF repository. So you don't have to know the details of what these functions are doing exactly. It's more important to just have a high level understanding of logically what it's doing underneath. So we also have a bunch of configurations that go into running this experiment. So what I've done so far is I've filled in a YAML file that contains all of our configurations that you can see on the right panel over here. So this YAML file contains a lot of the configurations, hyperparameters that we have in training this LBEF model. So that includes the paths to our data specification files, batch sizes, and so on and so forth. And in order to use these configurations in code, what I'm doing here is I'm manually loading this configuration file into a dictionary. So we will be able to refer to all of these parameters that we are filling in. And yeah, spoiler alert, later on, we'll look at a better way of loading in configurations. But this is what we'll start with from now. And then we also want to set seeds for our experiments. This is generally good practice because there is a lot of randomness that goes into training your model. So for instance, we want to split our data set into train, validation, and test. That splitting actually involves randomness. And in order to make sure that we can always recheck our model results and can always reuse earlier results, we want to control the randomness that we have in the training process. So what we typically do here is we have a seed, and then we want to apply this seed to different modules that we're using in the experiment. So I'm just going to copy paste these here. So for instance, we can control the randomness for the random module, for NumPy, for PyTorch, and so on. Finally, last step of the setup, we want to define our hardware. So that depends on what you have and what you plan to use. So in this case, I'm defining our hardware to be CUDA, to be our GPU on the Colab notebook. And you can feel free to define a CPU if you would like to use that. So that's it for our setup steps. And let's start walking through the 5 essential steps of training your model. So first, we want to prepare our training data. And here, we don't have to go into the details, but I want you to pay attention to 2 logical components. The first is we have the notion of a data set. So this data set basically contains your data. So in our case, that would be a set of image and text pairs. And using the LBEF code base, we have a helper function that would allow us to do that. And underneath this, we are basically using the PyTorch dataset class. Beyond the dataset, the other logical component is the data loader. So the data loader basically takes in the dataset and then repeatedly fetches batches of data from the dataset for you to train your model, to test your model. Again, here we will use a helper function. We don't need to dive into the details, but I would like you to remember that we first create a data set and then we create the corresponding data loaders for each of the data set. The second step of training your model is to define the model. And particularly because we're looking at a vision language model, we also need to have a tokenizer that tokenizes the raw text inputs that we give to the model. After having the tokenizer, we want to define the model architecture. So in this case, we are defining the LBEF model, and this is how we define the model architecture using their constructor. So we pass in model configurations, and we also pass in the text encoder as well as the tokenizer that we just created. And after defining our model, if we choose to fine-tune our model rather than training our model from scratch, we can choose to load our model, load the model weights from an existing pre-trained checkpoint. So here you can see that if we're setting our checkpoint configuration to be true, if we have this checkpoint path, then we actually want to load all of the weights, the pre-trained weights from this predefined checkpoint path. And then finally, we finish this function. And by calling this function, we're able to get a tokenizer and the associated Albeth model from our function. So note that in this second step of model training, we are defining our model architecture as well as any other supporting classes, instances that that support the model. The third step of training your own model is to define the training mechanism, which is the meat of model training. So here we first have a function that takes in our model, a particular data loader, whether it be training, validation, and test. We have some kind of optimizer. We have our tokenizer, and we have a lot of other supporting configurations, such as number of epochs, the current epoch index, as well as other configurations. So in this model training script, we first want to set our model to training stage. And then we want to define a lot of supporting variables like the step size. And we also want to define some variables that we want to keep track of during training. So in our case, we have 3 variables.
Kathy, quick question from the audience is, are you able to share the collab notebook right now in case people can follow along that way?
Yeah, of course. I'm happy to do that right now. Okay. Let me quickly. Oh yes, sorry, I just saw this question. Let me open up the. Yes, okay, I just shared this notebook to everyone. People should be able to access. Thank you so much. Okay. Okay, so let's come back to this. Earlier, we were talking about keeping track of some quantities during training in order for us to monitor the model training process. And also, we need to define the loss that we are training our model on. So in this case, we have actually 3 quantities. The first is an aggregate loss. This is the sum of all of the different losses that we care about. And the losses that we care about here are these 2, which are named ITA and ITM. So you don't have to know the details of these. If you're interested, feel free to check out the Albeth paper. But just very briefly, ITA is a contrastive learning based loss between the image and text. And then ITM stands for the image text matching loss after in a multimodal representation of our image and text. But for the purpose of this walkthrough, you can just imagine that we have 2 things that are valuable in determining the model performance, these 2 losses. And overall, we want to optimize our model by reducing the sum of these 2 losses. That's all you need to know for this session. And then after defining this, we are taking batches of data from our data loader. So for our model, we have some image data, we have some text data. And for the image data, we just do the standard processing where we convert the data to our intended hardware device. And then for the text data, we need to do an extra layer processing where we need to pass the raw text into our tokenizer, and then we obtain the corresponding text tokens. And then after having prepared the inputs that go into our model, we can define the main training script. So what we do here is we want to do a forward pass on the model. And then after doing that forward pass, we want to compute the associated loss of the model on that input. So what we do now is we have 2 losses, ITA and ITM. And we want to pass the image and the converted text input, as well as some other parameters into our model. So what this step does is it does a forward pass and it computes losses that would allow us to do back propagation on. And as I mentioned earlier, we might care about multiple loss functions. So we, in this case, we'll be looking at the sum of these two different loss items. And we want to train our model on this overall loss, the aggregate loss. And then after computing the loss of our model on this particular batch of data, we want to first clear our optimizer. And then we want to run back propagation on our model. So this is very template PyTorch code, but basically this is the meat of our training logic. This is what's helping our model learn. And then finally, after defining these training steps, we also want to make sure that we are keeping track of the important values that we just looked at. So the aggregate loss, as well as the separate losses. We want to make sure that we have we're keeping like a running average of these losses during the training process. And then finally, this training function corresponds to one particular epoch of training. And after this particular epoch, we want to return our running average of losses so that we can reflect on how well the training process is working for this epoch and how well is our model currently doing. So that wraps up the training loop. Beyond the training loop, we also need to define other supporting things. So the first thing is we need to define an optimizer. So for instance, you might want to use the SGD optimizer. You might want to use AtomW. This is something that you can try out. In addition, we also often want to have a scheduler because we want to have more flexibility than having a fixed learning rate. So we often define a scheduler that adjusts the learning rate dynamically based on model performance. And there are a lot of schedulers that you can find out of the box from PyTorch. So next, we move on to the fourth step of model training, which is defining the evaluation mechanism. For this, we won't go into the code because we're more focused on the training step, but there will be a very exciting lecture on model evaluation later today as well. So please remember to check that out. For our purposes here, just know what the evaluation mechanism is doing. So first of all, we can see that our evaluation script follows a very similar signature as our training function. It basically takes in the model, the data loader, and other supporting variables, as well as our configurations. And what we are doing in this configuration, in this evaluate function, is we are computing the image retrieval metrics, as well as the text retrieval metrics that we are interested in evaluating our model on. So I will scroll all the way to the bottom. We can skip all of the details of exactly how those are computed and just look at what results we're keeping track of. So here we're keeping track of the text retrieval at 1 metric, the text retrieval at 5 metric, the text retrieval at 10 metric, as well as a mean of all of these different metrics. And similarly, we have the same set of metrics for image retrieval. And then finally, we have an overall R-mean metric that allows us to summarize performance across text retrieval and image retrieval. So when you are training your own model, this is an essential step, designing what metric values you care about and what metrics values you want to log. Because oftentimes we might not have a single metric that works perfectly for your downstream task. Oftentimes we want to look at different dimensions of the model so that we can analyze the model better. So for instance, we might end up with a model that does really well on text retrieval at 5, but somehow does poorly on image retrieval at 1. That's entirely possible. So it's important to design a comprehensive list of metrics that you can evaluate your model on. And then after defining all of these different components, at the final step of training, we can put everything together and start training. So I will point you to the essential components here. The first thing that we want to do is, again, we want to be able to load some of the configurations that we defined. So the max number of epochs that we'll be training our model on. And we also want to keep track of what's the best performance we have seen so far and what is the corresponding epoch. And then we can start training. It's usually a good idea to also log your training time just to know how intensive the training process is. And then the main training loop will basically be looping over each of the epochs that you want to have overall in your training. So maybe you want to train for 10 epochs, for 100 epochs. And then within each epoch, we basically call the training function that we defined earlier. So this training function trains the model on all of the data in one epoch, and then returns a lot of training statistics that we have just seen. So in our case, that will be a dictionary of 3 different losses. And then we want to evaluate our model after we've trained the model for 1 epoch. And we don't have to look into the details here, but just remember that val results and test result correspond to this dictionary. So basically, it tells us how our model is doing towards the end of one particular epoch in terms of all of these different metrics. And then we can collect all of these different statistics here. So we can collect our training statistics as well as our model evaluation results on validation and test. And then we can wrap all of these up together. And then finally, we also have a learning rate scheduler. We can update our learning rate using the scheduler towards the end of each epoch. And then outside of this for loop, we can wrap up our model training. So we can define the overall time of this training, and then we can do some logging from there. So this actually shows you the essential steps that go into building your model. So we define our data set, we define our model, we define how we train our model, we define how we evaluate our model, and then we basically put all of these components together, and you have yourself a full training script for developing and evaluating your model. So that's the first part of this live coding section. As you see, we have a lot of other unfilled sections in this notebook, and we will continue doing that in the rest of this lecture. So let me quickly switch back to our slides. So as a recap, here is a list of PyTorch references that you can look at for completing these 5 essential steps. So we have the PyTorch dataset, the PyTorch data loader, as well as the PyTorch NN module, which includes a lot of predefined layers, as well as loss functions that you can use out of the box. And we also have the optimizers that PyTorch provides. So if you're unfamiliar with these, feel free to refer back to this page for API reference on PyTorch. And I will make sure to share the slide deck with all of you towards the end of the session. And then next, let's try to tackle our second motivating scenario, which is if you know how to write all of these, how do you improve the quality of your code, make sure that it's clean and reusable? So let's switch back to our notebook over here. And there are 2 essential things that I want to point out for this section. The first is modularization. It's always important to break your code down to multiple small logical components. The smaller, the better. So in our case, we are, for instance, designing a train function that handles all of the model training process within 1 epoch. And obviously, this code actually can be improved further. So for instance, we can actually break our, we can define the logic we need to execute within 1 data batch as a separate function, as a separate helper function as well. But the key thing that I would like you to take away is always try to break down your code into manageable components. These have a number of benefits. So for instance, when you want to make a certain adjustment to your training script, then the only thing that you need to do is modify this particular function that contains whatever you're trying to change. You don't have to copy paste your modifications to multiple places of the code, which can be very error prone. In addition, when you break down your code into small logical components, it's also easier to test your code. So you can have small sanity checks on your code for every small building blocks. And that would also allow easier debugging and easier future modification of your code. So that's the first thing. The second thing that I want to highlight here in terms of writing cleaner scripts is always avoid hard coding. Avoid hard coding at all costs. As you can see here, within the training script, we never really referenced any configurations or hyperparameters that we can tune for the model. We're always using a dictionary called configuration, and then we're indexing into this dictionary to get the configurations that we want. In addition, it's also good practice to not expose all of the parameters that you have in your configurations. So for instance, you can imagine that in this training function, we can basically expand config here. We can write, oh, there is step size, there is alpha, there is warm up, there's all these parameters. We can explicitly list them out here, but that's actually not good practice because that makes it hard to modify this function later on. Because when you need to modify this function, for instance, you want to add an extra configuration, when you need to do that, you not only have to change the function signature here, you also have to change every invocation of this function and pass in that extra parameter, which will be very cumbersome. So it's good practice to pass in like a package of all of your configurations so that in the future, when you need to make changes to your configuration object, all of the function calls to this function can stay exactly the same. So yeah, just to very quickly recap, the two things to note here in terms of writing clean and reusable code are modularization and avoiding hard coding. In addition to that, even though we are doing this live coding session in Colab, in general, it's actually better to use Python modules, Python scripts to organize your code. The reason why we use Colab is it's clear for demoing and it's clear for playing with your code and getting some preliminary results. But ultimately, when you want to build your model and when you want to run a lot of experiment trials, it's always good to have Python modules. Why? The first thing is Python modules can be cleanly organized into hierarchical structures. So sample directory structure might look like this. You might have a README file that explains what your code does. You might have a dataset directory that holds everything that you have for creating data sets and data loaders. You might have a model directory that holds how you define your model, let's say the alphabet model, and all of the supporting components. And you might actually have different variations of the same model. We have a utility directory structure that contains helper functions. We might have a train directory that contains your training scripts and all of the supporting functions. We have a configuration directory that allows you to keep configuration files. We can have a logs directory that keeps track of all of the intermediate model outputs. And we can have also a plots directory that keeps track of visualizations, the images that you generate, the histograms, the scatter plots that you generate during model development. And we might also finally have a training script that serves as the entry point to your training logic. So with this kind of directory structure, you can very cleanly organize the different logical components of your code. And when your model gets complicated, your directory structure will allow you to better manage all of the different complexities you have with your model, with your data. Another benefit of actually having Python code, Python modules instead of notebooks is Python modules can be very easily versioned. You can use, for instance, GitHub to version control your scripts. So you'll know exactly what changes you're making at every time point in your development process. In contrast, notebooks are not so great with version control. When you make changes to a particular cell, the version control system not only logs those code changes, but also a lot of the metadata, a lot of the runtime data that happen behind the scenes in your notebook. So it's hard to keep track of exactly what you're changing throughout this process. In addition, separate Python modules would allow you to do separate testing. So for instance, for every module, you can do sanity checks. But with notebook cells, it's also hard to do that. So after getting a start on Colab notebooks or a local Jupyter notebooks, I also strongly encourage you to shift to organized and versioned Python modules when you deep further into this model training process. So that concludes our first and two motivating scenarios. Now let's dive into motivating scenario number 3. Experiment management. So as you've seen just now, in our kind of scary configuration dictionary, there are so many things that we can tune for this model. So how do we make sure that when we do a lot of trial and error on these different variables, hyperparameters, how do we make sure that we are logging everything we need to remember for each experiment trial? So let's actually do a very quick walkthrough of our training script again. So we have all of these configurations. Most of them can be tuned to better train your model. So let's make sure that we keep track of these configurations. So the first thing that we can do is in the final training script, we want to define a experiment-specific directory. So what we're doing here is we are defining some overarching output directory that's supposed to hold all of our data and all of our artifacts. And then we want to give a name to the particular experiment that we're running. So this is the series of experiments that we're currently running. In this case, I'm setting that to demo. And then we also want to define whether our current directory is a training directory versus, let's say, just like an experimental directory or a test directory. So we want to do that. We want to make sure that everything that we generate in this model training process is properly saved into this experiment-specific directory. Beyond that, we also want to save our model checkpoints. This comes in 2 reasons. The first is our best model might not be the model we end up getting at the final epoch. So we want to be able to save a potentially intermediate model as our best model. The second reason we want to do this is we always want to reuse our earlier results. So for instance, after training maybe 10 models, you might suddenly think that, oh, I forgot to evaluate our model on this particular metric, but I want to go back and do that. Then you don't have to restart your training process for these 10 models. You can just use the saved model checkpoints, but run additional analyses on them. So this is why we're doing that. And in particular, the code that we'll be using is the following. So what we can do is we can keep track of the best result that we've seen so far. Maybe in this particular training setting, the metric that we care most about is the RME metric. That what we can do is towards the end of every epoch, we can compare the current validation result with the best result we've seen so far. If we're getting a better model than prior epochs, then we can basically save the model itself, the model weights, as well as the other supporting parameters And then we can save that locally to the best model checkpoint that we have seen so far. So in this case, we're using something called checkpoint best. And then we are updating the best results so that we can iteratively do this process in later parts of the code, in later epochs. In addition, beyond saving the best model checkpoints, we also want to remember what configurations led to this checkpoint. And we also want to keep track of some basic performance results for this model so that whenever we need to analyze the model, we don't always have to recompute things. So what we're doing here is we can also save configurations and model performances. So first, let's save our configurations. So earlier we defined our configurations into this config dictionary, and then we can basically save that, let's say, to a YAML file into our log directory that we just set up. In addition to the configurations, we also want to log the model performance that we generate during this training process so that we don't have to recompute these. And we can log that into a separate performance file, and we will keep track of this so that we can easily run downstream analyses from these results. So after adding in these three pieces, so saving configurations, saving model checkpoints, saving model performances, what we end up with is a very clean, organized set of artifacts that allow us to double check our experiment results and also allow us to use these different models. So let me go back to my mounted drive. So by adding these components, we would have the following. So let's say we defined our logging directory, our large logging directory to be output. And let's say we are currently running a bunch of training experiments, and we call this set of experiments train. And then we want to run a lot of models. We want to run a lot of model training processes. And let's say we have run one. I have prepared one beforehand to show you. So let's say this model is called demo 01. Then within this output directory, what you'll see is we have this configuration file that gives us a snapshot of what gave rise to this model, to this experiment. We also have a log file that logs the stepwise outputs of our model. It's also generally good to always keep track of like other information such as sizes, time information, as well as warnings and errors in this log text as well, so that if, for instance, something goes wrong in the training process, we can always retrace back to the problem. And we also have this performance file that keeps a dictionary of all of the different model metrics that we have for the best model that we're saving the checkpoint for, so that when we want to analyze results for this experiment trial, we can just refer to this performance text without having to reload the model, rerun the model. So let me switch gear a little bit. So beyond that, I also want to introduce you to a tool named Hydra. So earlier in the training script, we have seen that we are manually loading in the configuration files. So let me quickly go to that. So earlier, what we're doing is we're manually defining a set of configurations, and then we're assigning those configurations to a dictionary. That's actually pretty elegant. What if there's a better way to do this? So what we'll do here is I have prepared a training script that basically contains the full notebook codes. So essentially, following the guidelines that I just mentioned, I'm moving all of these codes to, let's say, a Python script called train.py over here. And these are all of the exact same code that we've just seen in the notebook walkthrough. Remember earlier, we were doing these steps to manually load our configuration. But now I'm going to introduce you to a tool called Hydra that would saves us the trouble. The only changes that you need to make here are you want to add this hydra.make decorator to our function that runs model training. So let's say we call it main. We basically add this this decorator. We define the path to our configurations. Our configurations is put into this configs folder. And then we also put in the name of our specific configuration YAML file, which in our case is retrieval flicker. And that's basically all you need to do. By just adding this one line, Hydra will automatically load the configuration files for you and insert those configurations into this input parameter of the function. So you don't need to do any file IO on your own. You just need to add this, and then you can use this config as we've just seen. And that will be very, very convenient. So what you can do is you can basically run a command that says python train.py, and then this main function would automatically get all of the configurations that you defined in your config file. Another point that I want to mention with Hydra is Hydra also supports a bunch of other helpful functionalities for managing configurations. One is, in our case here, if we want to modify our configurations, we actually have to open the file, and then we have to manually change some of the values here. That's actually inconvenient if you want to run a lot of experiments and you want to do this process very quickly. So what Hydra allows you to do is you can very easily override your configurations on the command line. An example of this is shown here. So let's say we have a configuration file. Notice that the configurations can come in hierarchies. And we define this main function, and we have this decorator that helps us load the configuration file. And the very default way of launching our training script will be to say Python, the script name, but then you can also override. For instance, you want to try out a particular learning rate, then you can just override the learning rate parameter on the command line, and then Hydra will automatically tweak the configurations for you without needing you to actually open the configuration file and adjust the configurations. And for more helpful functions of Hydra, feel free to reference these links here when I share the slides later on. The other thing for other important things for organizing multiple experiment trials are setting up a directory structure, as I just showed you. So as a recap, we want to have some kind of logs directory that holds all of our experiment outputs. And we can define some kind of experiment trial group. So all of these trials fall into one particular group. Maybe all of these trials are related to one particular model architecture. And then within this group directory, we want to have a separate directory for every trial that we're running. So recall in the walkthrough that I just showed you, this will correspond to, let's say, demo 01. So that's trial number 1. And then within these directory, we can save the configurations, the model checkpoints, the final model performances, as well as a bunch of intermediate logs. Beyond setting up a directory, another good practice is to have a script that automatically aggregates experiment configurations and results. Because ultimately, when we're trying to improve our model, what we're doing is we want to figure out what set of configurations can lead to better results. So essentially, we want to put configurations and performance results together so that we can properly analyze how to improve our model. And with the directory structure that we've just seen, you can very easily do this by just going into each of the directory by experiment ID, and then taking essentially the configuration YAML file and the performance YAML file. After aggregating these results, one other trick is to actually use a Google spreadsheet pivot table to organize all of these results together and visualize them. So sample Google pivot table would look like this. And let me actually show you this example live. So here I have created a dummy pivot table. So let's say we have run 4 different experiments, and then we are tuning 2 particular hyperparameters, the learning rate and the optimizer that we're using. And for evaluating the model, we might be interested in 2 different metrics. Let's say the R-mean and the text retrieval at 1 metrics. So with these results, we want to know how our model is doing and how we can further improve our models. So the way we do that is we can use insert and this pivot table function to get a pivot table generated from these raw results. So because of time, I will just directly go through the pivot tables with you. So when you run the pivot table function on that table, this is what you'll get. And after getting this, you have the option of ranking your models, ranking different experiment trials based on different metrics. So let's say we care about R-mean the most. Then we want to rank R-mean first in a descending order. So you can see that the top model would be the model that's doing best according to the metric that we care about the most. And then you can look at what are the corresponding hyperparameters that help you create these models. And then in addition, if you care about other metrics, you can of course adjust the order of your metrics so that you can basically re-rank your model and then learn what model is doing best under a different metric. So because I'm running a little bit out of time, I will go a little bit faster here. So yeah, remember to use a pivot table for organizing your experiments. And then finally, let's look at some additional techniques for improving model training. And just to very quickly summarize, we want to analyze these aggregate results and identify patterns and trade-offs. And the key thing that helps you better understand your model is actually to log a lot of intermediate metric values and log a lot of supporting information. The rule of thumb here is the more you log, the better, because the more transparency you have into your model. And just very quickly over here, let me show you how to do a lot of these logging. And the tool that we will be using here is called weights and biases. So the most important thing here is during this model training process, we can have we already defined our log stats variable from before. So as a recap, this includes our training statistics as well as our evaluation results for validation and test. So with this log stats, we actually have a lot of information about how our model is doing right now. So we can basically call this function from the weights and biases library, and we can log all of these statistics for this particular epoch. Going beyond that, we might actually want to do more than just logging scalar values. So within a particular training script, we also have the option of, for instance, logging our examples. So in our case, our training examples are images and text. So we might be interested in knowing what images and text our model is doing poorly on. So if we want to do that, we can have something like this, where when the loss is bad enough, we want to check out what the corresponding images and text are. So we can have this extra script that logs the images as well as their associated text as captions during our model training process. And again, we can easily do this with the weights and biases log function. And going back here, here is actually a list of interesting references from weights and biases that you can use that would allow us to do these type of logging. So usually we would use this init function before we start running any experiments. We would use this log function to log either numeric values or more complicated values like image, text, even histograms. And then we also have this watch function to continuously monitor certain model statuses. And also one thing that I want to highlight here is weights and biases is a very helpful platform that allows you to do a lot of other things. Meanwhile, you can also explore other tools such as TensorBoard, which also allows you to log and visualize results. So feel free to try these things out and pick the one that you like the best. So let's just quickly revisit all of the essential components that we had for building a model. So with data, we used Flickr 30K. With model, we used the Albeth model. With training, we are training on the two contrastive losses, the image text contrastive loss and the image text matching loss. And then we were evaluating on image and text retrievals. And in terms of variables, we defined our different hyperparameters, different model architectures. And in terms of result analysis, we looked at retrieval metrics, we looked at pivot tables, and we also looked at sample images that we can log during the training process. And finally, in terms of utilities, we have logging functions, we have visualization functions. So very quick summary, in this lecture, we have looked at how to train models, how to write better code, how to manage experiments, and how to improve your model by logging a lot of intermediate values to better understand your model. And then we have learned to use these tools, PyTorch, Hydra, Google Pivot Tables, as well as weights and biases. And also going forward, let's always keep these principles in the back of our mind, maintaining good code quality, reproducibility, as well as to be mindful of tracking your experiments and scaling your experiments. And there are also many other exciting topics to explore in this. So for instance, data versioning and model versioning. And also for the AI research intensive, there are many other exciting topics that you can explore. So here are the references to this lecture. And thank you so much for coming to the session today.
Thank you, Kathy, for the wonderful session. Your coverage through a walkthrough of exactly how things happen has, I'm sure, made it very clear to everyone in the audience how this works. So thank you.
Thank you.